Hello, Mr. Miss Ryan, are you right?
No.
You're not right? Okay, so what's binary tree? We talk about binary
The
tree.
binary tree.
Yeah, boy.
What's binary tree? Come on, Eric, come on.
It's a tree
Tree, okay.
which is binary.
A tree which is binary. That doesn't make any sense. Come on.
The binary tree is a binary tree.
It's a data structure, yeah?
That's a binary tree.
So you can also say it's a
That doesn't make any
DAG.
sense.
DAG, what's DAG?
DOD, DAG.
What's DAG?
Directed
Cyclic graph.
Yeah, it's directly a cyclic graph. It doesn't have any cycles. It's a graph. It's a data structure.
It
It's a
doesn't
graph.
have any notes in it.
It doesn't have values in it, but that's fine. So
Why?
which one? Yeah, I put a value anyway. And what's the
But
which one is the root?
the top one.
Okay, and the root doesn't have any parents. Okay, which node? What are the nodes that doesn't have any kids? What do we call them? Leaves. Yes. And how many node? What's the maximum number of kids that a node in the binary tree can? Okay, you got it. Yeah, well done. Okay.
0.
If it's 0, then it's just a dot. Yeah, it's just a dot. It's not forming a tree. Okay, so today
A dot is a tree.
a node is a tree. Yeah, it's
dot
it's
is
a very
tiny
special tree.
from first sight.
Yeah.
So
So you see as a dot.
what's balance? If I say balance binary tree, what's
Like this. Like this. You get like this. Whoa. Whoa.
What's balance? Okay, what's balance mean?
You
Yeah, you like this balance, yeah? What's
Yeah,
unbalanced?
you like this.
Okay. What's unbalanced?
unbalance is the opposite of balance.
Yeah, it's the opposite of unbalanced. So can you
Whoa.
okay? So can you say a very very unbalanced tree, binary tree? So it's an extreme binary.
Stick.
It's a stick.
Yeah.
Okay, so it's a stick like that.
Yeah.
Okay, this is extremely unbalanced all this way. Okay. So can you draw a tree which is balanced? Yeah, this is balanced. Okay. So a binary tree is balanced if the height of its left on right differs no more than 1. Okay. So at any node, the difference of height in its both left and right tree is no more than 1. For example, the depth, the height, yeah, the height. Yeah? So d left minus d right, the absolute value is smaller or equal than 1 for any node. Yeah? What's this absolute value? What's this absolute value? Remember? What's this? A, B, X, X. What's absolute minus 3 equals what?
Sorry.
Yeah. So it's
Keep.
so look, this is the line of numbers. So in the middle that's 0. Yeah. This is infinity on the left, on the right. So absolute value is like the distance to this 0. Okay. So for positive numbers, absolute x is x. For the negative numbers, the absolute x is what? For the negative number, the absolute x equals what? Ryan? Anybody?
X.
No, for the negative numbers. Positive is absolute x equals x. This is the distance to here. If x is negative, what's the distance to here?
X.
X is negative.
Then X.
Minus 3, what's minus 3? You said 3, what's negative? X is minus 3, so what's the distance to the 0?
That thing.
Yeah, that thing, what's x? What's that thing? X is minus 3, so what's that thing? What's this thing? What's equal 3?
But that's X.
What do you mean? This is x, yes.
Yeah.
If x is
Then
positive.
you said X is negative.
Yeah, what I'm saying, if x is positive,
Yeah.
this is x. If x is negative, so what's this?
Positive X.
Okay, so you said positive version of x.
Yeah.
Okay, so
I
x
don't
is
know
minus.
I don't know how to say it.
Okay, x is minus 3. So what x equals the 3? Come on. X equals minus 3, so what kind of X? Positive. What should I do with?
You get rid of negative sign.
Okay, so what if I get rid of negative sign? So what should I do with the X?
You shall
What should I put in the front? Come on.
negative.
Negative. Okay, so that's what I'm looking for. If X is negative, absolute value of X equals minus X. Okay. Okay. Yeah. So do you get this point? Yeah. What's the definition of the balanced binary tree?
Balance.
What's the definition of balanced binary tree? Come on, I will just explaining. Okay, I'm going to write a few balanced binary tree and you tell me, okay? Or if not,
On the video of making the house, sir.
is this a balanced binary tree?
No. No. Yes.
Why you said no and yes?
Yes.
Okay, why is it yes?
It's because it's one.
Yeah, it differs by one. Okay, good job. Is this a balanced binary tree?
No.
No? Why is it not?
Yes.
Yes, of course. This is it? Yes, this is 2, this is 1, right? Yes. How about this?
Hey.
Is this?
No.
Yeah,
No.
that differs by 2. Right? How about this?
Yes. No.
Yes or no? Come on. What's the
Uh,
Is this balanced? Come on. Any node, if the left and the right, it differs by no more than 1. So if we look at the root, what's the
yes.
Sorry?
No.
Why is that?
Yes.
Come on,
No.
don't guess.
Yes.
Okay, I'm here.
Yes.
What's the
No.
depth of the left subtree?
Um,
Including it, right? 1, 2, 3. What's the right subtree?
nothing.
Okay, so what's the difference?
One.
1?
Two.
Sorry? How many what's the depth of the left subtree? Okay, that's okay. 2. What's the depth of the right subtree? Nothing. So what's the difference? What's the difference?
Two.
2. So it's not a balanced tree, okay? Okay, one more. The last one. Is this a balance?
Yes.
It's a balance, yes.
Yeah. Oh yeah.
That's 2. That's 1, yes. Okay. Okay, that's it. So, okay, so we first of all we can. What's your approach? I mean, what's our approach of doing that? What's our approach of doing that? What's our approach of solving this problem? I mean, we need to check every node for the depth of the left subtree and the right subtree. Do you still remember how do we get the the depth, the height of the binary tree? Yeah. Do you still remember? Define. Okay, we can use the first the recursion. Okay.
Yeah.
Root. Okay, can you complete this function? Come on. Every line. Come on. Depth.
Depth.
This function returns the height, the depth of root of the tree with the root. Yeah. So if not root, we return what? Come on.
Nothing. True.
The height. What's the height of it? An empty node. What's the height? Height, the depth. This is 1. This is 1 node. 1. So this is 2. This is 3. So empty is what?
Empty is nothing.
What's nothing?
True.
A number.
Doesn't right.
Yeah. Okay, so now we want to return the height. Okay, so return the height. So if a node, what's the height of this node of this tree?
3.
1, 2, 3, 4. Yeah, this is the bigger. Yeah. So look. So this this is the root. Yeah. This is the right. So what's this? What's the height of this bit? If this function is depth, what's the height of this bit?
The height of that is 2.
Yeah. So how do we call it? If we have this function to return the the height of this entire tree. We pass the root into the depth function. That will give us the height of this tree. So what's the height of the left tree? What's the root of a left tree? Depth what?
Root.
Root what?
The left.
Yeah. And what's the right bit?
Depth. Root. The right.
Yeah. Eh? And what's the tree of this whole bit? Okay, so look at the left equals depth root of left. Yeah, we call it recursion, yeah? Right equals depth root of right? Yeah? And then we should return what? Return what? Now this bit is left. Now this bit, the value is right. So what's the value for this root node? You should pick which one? The what? What's the height of a tree defined? It's the maximum. Okay, so return maximum, left, right, and I need to plus what? Left, right, plus what? Plus how many? The depth. So we know that the tree, the depth, the level, the depth of the tree of the left is left, right is right. And if we have one more node, what's the level going to be?
1.
So plus
0.
1. Okay, why you plus 0? Plus 0 is nothing.
Yeah,
Okay.
this thingy.
So look, we have this, yeah? Okay? So this is a useful function for us to determine if a tree is the balanced. Now we just have to put this, look, if this function is balanced, yeah? So how do we check if it's balanced? If we are given this function, B-A-L-A-N-C-E, balance, root. Okay? So if the root is none, or if not root, then we return true, okay? If the empty node is balanced. Okay, then if this tree is balanced, the left tree must be balanced, right? The right tree must be balanced, right? Am I right? Make sense? Yeah, if the left tree is not balanced, then the entire tree is not balanced. Am I right? Do you agree? If right tree is not balanced, the entire tree is not balanced. Agree? So then I can say return. I need to say is balanced. I call it cell, yeah? Balance.
No, you don't.
Root of left. And okay, and is balanced. Root of right? Okay? This tree needs to be balanced. This tree needs to be balanced. And the depth of the left and the right is no more than 1. Right? Make sense? So at any point, because we're calling itself, at any point, at each node, because look, its balance is calling itself, it's a recursion. Right? So we need to make sure every node, in terms of every node, the depth of the left tree and the right tree is no more than 1, the difference. So we need to put here the depth of root of left, yeah, and the depth of root of right minus depth of root of right smaller equal than 1. Okay, smaller equal than 1. Yeah. The time complexity for this one, you tell me is it ON or no or more? Come on, look. I need to check each node, and for each node I need to recursively call this function to find out the depth of the left and the right tree. Sorry? So one question, for each node, do we have to visit, how many times we visit one node? For example, if I want to visit, how many times I will visit this node, the left node? 1, more than 1, to answer. look here, I'm calling this function is balance. More than one. Yeah. Because look, it's balance Luda left. We call it. We definitely visit this. Right? And the depth Luda left. Definitely visit it. Right? So this complexity, okay, it's a little bit out of scope because it's a little bit complex. Okay, it's O and log n. Okay, because this is the balance. You know, usually balance tree. The problem is what? The problem is that for each node, we are calling this function. This will take another O(n) time in the worst case, right? We take another O(n) time to find out the depth for each node, right? So this is a top-down dynamic, top-down recursion. Yeah, because look, we top-down. Yeah, we starting from root top-down. For each node, I need to check if the depth of the left and right tree is no more than 1. And I need to call the recursion to check if this subtree is a balanced tree, okay? So this is top down. Look, I want to find out if this root, the tree of starting from the root is the balanced tree, right? Yeah? So then I need to go down the tree and to the leaves. To find out if the tree is the balanced. So this is top down, right? Yeah? So we can do better. Come on, everyone. So yeah, look at this function. Yeah, look at this function. I'm talking about this function. Yeah, just this function. Depth. Yeah, this function. Ryan, don't sing. This is
I'm not singing.
Okay. So look at depth. What's this depth doing?
It's doing that you give him a depth.
Sorry?
You give him depth.
Yeah, you got in the depth. Yeah. Okay, so at any point, if we going from to the leaves, yeah, to the leaves, and then if we go from the bottom to the up, in this direction, how can we do it? Look, all I have to do is to add one thing here, to check, right? So look, if this function still does what it's supposed to do to return the height of the binary tree, right? But if at any point we find out, look, we already know the left and right here. Yeah? If at any point we find out that the difference between the left and right is more than 1, then we know it's not a balanced binary tree, right? Because the balanced binary tree, the definition is that for every node, right? For every node, it has to be satisfying that the depth of the left and the right is no more than 1. Yeah? So here, then we say if absolute difference, okay, absolute value, ABS, left minus right is bigger than 1, right? So this is not a balanced binary tree. So we need to set it somewhere. Let's say self.answer equals true. We set it to true, and then we can set it to false here. Self.answer equals false. Okay? And then we can just return self.answer. Make sense? So yeah, Ryan, do you understand, Ryan?
Okay, yeah.
Yeah. So what's the time complexity for this one? Look, if I just adding a check. Yeah. If I'm just adding a check, look, what's the difference? The blue one, the green one.
It's.
So this function is to get check the depth. Yeah. Look at this is the function depth root, and then will be here and here, right? But at any point, in terms of this, I'm standing at the root, and then now I know the left and the right tree, the depths are left and right. And at any node, because look at each node, each node will be visited once, and at each node we know the left and right. Yeah. So if at that point the left and right the difference is more than 1, then we know it's not a balanced binary tree, and then we can set the flag somewhere, set the answer. Yeah. Okay. Or we can rewrite this function. Yeah. We can rewrite this function to return. Okay, I'm not going to expand here, yeah, but it's a similar idea. So we can return this function, for example, to return if the left tree is the balanced tree, return the tuple, yeah? Return the tuple. The left tree is balanced and the left height. The height. Okay? If no, we return the height. We return if it's balanced tree or not. The first value of the tuple. The second value is the height of the tree. And we can return these two values for the depth. So depth will return what? Return a value is balanced. Let's say is balanced B, and then that will be C. Okay, and then here we can return AB as left minus y is smaller than equal than 1, and the second value of in the tuple will be the height, right? And then if not B, then return false, 0. If not C, then return false, 0. Okay, so this is another similar idea, yeah. So and then we can return the depth root, the first value, which is indicating if the tree is balanced or not. The second value of the tuple will be the height. The first value will be indicating if the tree is the balance or not, right? This is also okay. Make sense? So which one you think is better? It's good. You can remember.
The shorter one.
This one, yeah. We talked about this before, yeah? The computer depth, long time ago in the first maybe 50 days. Yeah? Yeah? Got it? Okay. The time complexity for this one is O1, okay? O1, because each node is visited only once. The space complexity is also O1 because we are using the recursion, right? This is kind of top-down, bottom-up, yeah? Right? Because it will be reaching the end, which is 0, and then you build up from the bottom up, right? Make sense? Do you understand? Yeah? Okay, let's say for today, do some ending, please. Do some ending. Ready, steady, go. Are you okay? Yeah, do some dancing. Come on. Bye bye.
Bye bye.
Bye bye. Bye bye.